3, 2, 1. This is a video series intended to illustrate and explain the basic principles behind Brayton cycle, which is a ideal gas turbine power cycle. This cycle is mainly used in aircraft propulsion and electric power generation during peak periods and emergencies due to its fast response time and low cost. The peak periods, we need something to get injected to the grid in order to get power during just the peak period, and then this power must be removed from the grid again to get to the normal operating power. This is the peak power. And also this peak power have a special tariff applied to the contribution of this peak. This is the ideal cycle for the gas power cycle, gas power engines, as we already mentioned. Two very important hints for this video series is that this video, the schematics used and the graphs used for this series are not necessarily the practical ones and not necessarily the ones that are used in real design and engineering, but their intent is for illustration only. Second, most important thing is that the context of this video series is for a basic thermodynamic course where basic thermodynamic cycles are introduced. The Brayton cycle cycles and its modifications are tackled once more in propulsion and jet engines courses. Of course, it's a very long way before you can implement something like this and know the practical application of it. So the context is basic thermodynamic course. First of all, we are going to get introduced to the gas turbine engine itself. The actual thing that we're gonna simplify and a simplified version of it. This is a single stage gas turbine engine. It takes fresh air from the surrounding, from the atmosphere, gets it into a compressor, raises its pressure, then raises its temperature by mixing it with fuel and burning it. Then this combustion product, which is at high temperature and high pressure, are passed through a turbine to extract work from them, and then the exhaust products are exhausted away and they are not recycled back in the actual stage, single stage. It is a single stage. The actual one might be a multi-stage from this. The idealized one, which is intended to aid the analysis of the Brayton cycle, is a closed cycle, not open like this one. The combustion, one of the main assumptions is that the combustion chamber and the exhaust stage are both exchanged with heat exchangers. So the heat is coming from outside the cycle. Here the heat is inside the cycle. This is an internal combustion engine. Here the heat comes out from outside the cycle. The working fluid is the same throughout the cycle. The actual one, the working fluid here for the compression is fresh air. Then in the combustion chamber, it's mixed with fuel and get burned. Then the combustion products are passed to the turbine. Another major assumption we make here that the flowing fluid and the circulating fluid is an ideal gas. Okay, the assumptions are here. Air standard assumptions that the floating fluid is ideal, is an ideal gas. The combustion and the exhaust stages are replaced with the heat exchangers, and it's closed, and the exhausts are for analytical reasons and for theoretical reasons are set to return back to stage one to get the cycle done again. Another assumption is that the cycle is composed of 4 internally reversible processes. We know that any reversible process is very hard or impractical to implement in nature without any reversibilities, because nature is by nature irreversible. So assuming that it's internally irreversible, just to simplify the analysis. And later on in another advanced courses, these assumptions are all going to be violated in order to see the impact, the actual impact of the application. Stage 1 to 2 is a compression stage, which is assumed to be isentropic. Also the turbine stage, which is an expansion stage, provided that the work is extracted during this expansion stage is also isentropic. The heat addition and heat rejection stages in these heat exchangers are assumed to be isobaric at constant pressure. Isobaric means constant pressure. Constant P. Okay. The diagrams on the PV diagrams, the P pressure and specific volume, and the TS diagrams look something like this. We're going to draw them ourselves in a minute. But we have to remember that. This is stage 1, compression, stage 2, gets heated, stage 3, pressure down, stage 4, temperature down, stage 1. We've already agreed on the assumptions implemented or used in this analysis. The standard assumption, called L standard assumptions, is that we assume that the specific heats are constant. Thus, the ratio between them, Cp over C subscript V over C subscript V, are also constant. The four internally reversible processes, and these are the diagrams we're gonna draw them ourselves right now. In this cycle, we have two types of processes. The compression and the expansion are isentropic. The heat exchanging processes are isobaric. And as we already know, that isobaric and isentropic processes are from the polytropic processes. The polytropic processes, we're going to write it over here, it's a side note. Polytropic processes are represented by the equation PV to the power m equals constant. Thus, when m equals 0, then this equation becomes P equals constant. Of course, not a constant, one's constant. And when m equals K, where K is the ratio between the specific heats, Cp over Cv, this equation becomes P, V is the specific volume, the volume over mass, to the power K equals 1/3 constant. These are the two processes we're going to use. So, on a PV diagram, the blue is not so bright, it's not going to make it to the video. So, we know for the PV diagram that we have two isobaric processes occurring at constant pressure. We're going to assume that this is our low pressure and this is our high pressure, and we operate between those two pressures. The other two processes are isentropic, and this is isobaric, as we agreed. P equals the isobaric process, the equation of the isobaric process equals constant over V to the power K. This is an inverse function, 1 over x, or 1 over x to the power K. So it's going to be represented by something like this. Already we know that these axes of the thermodynamic axes are already shifted, or we work in some region of any diagram, we don't get the whole diagram. If for example, this is the whole diagram and this is extended over here and over here, we might take a small portion of it over here to work with. Whether we're working with ideal gases, we're working with fluids, we come to this portion of the graph, and so on. So this is our isentropic processes. Those are our isentropic processes. This is isobaric lines. So between the isobars and the isentropes, there is our cycle. This is S low, this is S high, and the area included here is equal to the work net extracted. Of course, this is not generally true, but given our assumptions, this is true. And which, by applying the first law, also this is equal to the Q. Okay, we already know that the area in the PV diagram is equal to the work. Applying first law analysis to the whole cycle, we know that the Q net, Q out, Q in minus Q out equals to work out minus work in. So those sides equal to the area. including the graph. What's remaining is to set the convention we use for these points or states. We already know that these states are 1, 2, 3, and 4. Let's take, for example, the compressor stage. We know that the compressor stage takes place isentropically. And this isentropic process is performed between the P low and the P high. So the compressor itself is used to raise the pressure. So, and another notice is that most of the power generating cycles are operated clockwise. So we already knew that this cycle takes place like this. All these notes are useful to make your drawing fast, and it's all based on basic thermodynamic principles. Okay, we know that between P low and P high, compression stage, this is 1 and this is 2. Then this is 3 and this is 4. What's remaining is to draw this TS diagram. Let's erase this a little bit. The TS diagram. And here is the S. We have two isentropic processes. You're operating between these two. And given the polytropic discussion, another discussion with different coefficients and thus are applied to the TS diagram to get the isobars lines like this. This is P, this is P, this is P, all constants. We're going to operate between those two pressures, the high one and the low one. So we have isentropic, isobaric, isentropic, and isobaric. That's our cycle. What's remaining is determining these ones. On the TS diagram, it's also operated clockwise, so the arrows are like that. The area included using the same principle. We already know that the TS diagram, the area included for reversible processes is equal to the Q net. Applying the first law is equal to the work net. This area. Okay, we're all good. Between the low pressure and the high pressure, raising it's also logical. Raising the pressure of a fluid isentropically leads to a rising temperature. Temperature 1 and temperature 2. There's 2 points, 1 and 2. This is the third temperature. This is a very important temperature. This is the limiting temperature. This temperature confines the efficiency of the cycle. We will later on explain why. And this is point 4. Later on in this video series, we are going to talk about the limitations of the Brayton cycle, the limitations of this analysis of the Brayton cycle, the idealized analysis we implemented over here, and test the validity of these assumptions. Also, thus we're going to talk about the modifications done to the Brayton cycle on all of these stages and adding some extra stages to improve the efficiency and the work output of this cycle. Thank you.